Okay, welcome everyone for our practical lecture 7.1 in the Cloud Computing and Big Data course. We doing a little bit of practical lecture on using deep learning techniques in clouds, and this obviously could fill many lectures, but we picked a little bit in the first part where this is here the second part, really an idea how we do that in the Amazon Web Services. So we had the idea of virtualization using AWS AMI images. And it captures nicely the essence of having pre-installed software available in the images. So I don't need to configure PyTorch. I don't need to configure TensorFlow, particularly in the light of the fact that also the underlying infrastructure, let it be NVIDIA GPUs, for instance, need to have the same and good drivers that are required by these packages. And examples have been, for instance, Nickel, but also basically the CUDA implementations and so on. CUDA is the programming language of the NVIDIA GPUs. And then we moved the attention a little bit to another, let's say, service, while the infrastructure as a service level with the virtualization is still, of course, sort of the basics. And the AMI is, of course, a very strong and powerful service on that particular level. And we will come back to these levels actually already next week. So lecture 8, 9, 10 will be all about differentiating between infrastructure as a service, platform as a service, and software as a service, while let's say they're a little bit overlapping here and there. We will make the case for it. But then we shift really the emphasis from the infrastructure as a service level in part 1 to the software as a service level by having a fully managed experience in the SageMaker tool. SageMaker is really also a very powerful service. We touch here across just a little bit the Jupyter notebooks because that's something what you know, and captures also nicely how we now connect the different lectures 6, 7 in a way around, moving from basically the simple perception model to artificial neural networks and then to convolutional neural networks that should demonstrate a little bit the point of deep learning here. But let us come also to part 2, and this, of course, starts a little bit with sort of a sad notion what we had in the first part. We were using the SageMaker tool, and we were exploring that actually using artificial neural networks was already terrible slow, right? So the epochs we have trained there, this took quite some time, and we learned that the SageMaker resources underneath, basically, that we chosen were exactly very weak resources. And that was our instance, and I will make a case for it also in part 2. Hence, now we actually increase the computational complexity. We want to come back to our little bit of a machine learning overview, just to tell you again that what we had early in the course of the fundamentals here of the mathematical building blocks, if you want, from machine learning, this still is relevant also if you move to deep learning, right? So again, the point is also here, as we discussed in the first part, we get some training samples, we learn from them. We have luckily here a supervised scenario, for instance, also in our MNIST, which what we of course continue with handwritten character recognition, meaning we have the 2D input from the grayscale image, but also then the guiding label with the numbers. And we would say we learn about this probability distribution. So we're not going then from this training examples and try to learn, let's say, movies, right, in recommendation engine from Netflix. This would be a completely different probability distribution that gave rise to the X. Hence, we can only learn something which sort of makes sense and where we already have said we have also a certain pattern to expect. Then, of course, we know that in one respect, there was something creating this data, right, from the MNIST, is what we mathematically abstract in a way as an unknown target function, which is in reality rather a target distribution. I will come to that in a moment. But what we want to achieve by now using our solution tools, if you want, so things we know from our skill sets, and we talk about this a lot today in the second part here, where the hypothesis set is now crucial for you to pick. So you would pick a support vector machine, maybe for classification. Then you also pick a learning algorithm, which would be quadratic programming, for instance. We have seen the perceptron learning model and the perceptron learning algorithm. Now, when you talk about ANNs, the artificial neural networks that we had in part 2, we talk about the backpropagation, and deep learning has also a very specific type of backpropagation that we use. So hence, here the hypothesis set, we now thinking about in switching actually from artificial neural networks to convolutional neural networks. And that's what we want to do. And of course, here the cloud course, we want to also understand the computational complexity. And this means this learning algorithm now is something what we will look at. And also when we're going through the epochs in order to find the final hypothesis. So from all of these hypotheses, we want to find the kind of G that approximates F quite well. In order to do so, we also have to talk about the error measure a little bit. So we will see how that materializes today when we talk about accuracy again here and there. And of course, then we'll also plot actually some error and also see how that actually aligns very well with the training or the accuracy if you want. And then, of course, the idea was, as I said earlier, in a way for mathematical correctness, we rather learn an unknown target distribution because we do learning from data. So it could be that basically they're training examples where the same X goes in, but different Y's goes out, right? So this is something which in mathematics, if you know a little bit about a function, breaks a function. This is basically not anymore a function. Hence, we have the idea of having here a target function plus a noisy character that we have here on top. So much for the mathematical building blocks. And as I said to you earlier, a machine learning course is really something which might be the next step for you if you really like these topics. Machine learning courses go much more in all of these different building blocks you see here. And also at the end today, I have for you something called validation for model selection. And also in your assignment, you have a regularization. These are topics, validation and regularization, as we already motivated a bit, combating overfitting, which is one of the biggest problems we have in machine learnings to fight. So this, in a way, differentiates the experts from the beginner, if you want. And this is, of course, something which is very important. But in this course, we cannot teach all of that. However, at the end of today, of this second part, I also want to make the case for one specific technique called n-fold validation techniques, because they're also computationally a little bit more challenging than normal. Still very important and a very smart trick if you want to perform validation, especially if you don't really swim a lot in annotated or labeled data. So coming back to our problem here now in the second part, we said, okay, in the last part, really part 1, we picked a hypothesis set from our skill set, and we know artificial neural networks with 2 hidden layers is H1. We could have had 3 hidden layers or 1 hidden layer. This would be another hypothesis. Every time we change something from the layout of the architecture, from the amounts of neurons, not only the number of hidden layers in this hidden layers, all of these kind of hyperparameters and structural changes to the network is something we call hyperparameters, and we have to talk about it also later than in lecture 13, I think, at the end of the course, because it's also getting quite computationally expensive when you pick that wisely. So here we now pick the convolutional neural networks as yet another hypothesis set, right? So we want to find out, can we do better? Is this approximating maybe the function that give rise to the data in a better accuracy? And that's what we want to find out. Essentially what we did in lecture 6 already, but here the idea is now, of course, giving you an idea how we do this in Amazon SageMaker, and also nicely connect what we had as a set notion, as I said the last time, right? So we started with Amazon SageMaker, and as you see here a little bit again on the slide before I come to the practical, we took this T3 medium, right, which essentially is just 2 small CPUs, very cheap, but of course very little performance. So this turned out to be doable just in ANNs, right? So this is a bit a sad note, doing this with CPU. So this was the kind of thing where we said, well, that really wasn't a good idea. Now we want to understand what happens if you take the CNN model, right? We expect what we learned already before, much more parameters to train. So hence, this might be not so easy to actually go there. So let's pick Ohio, and then we go to the notebooks here, where there's already one that I created from our previous part. And I just open the Jupyter notebook here. So this is running already, and we have already uploaded the source code for it. We have been running the ANN model, the last part. Now let's go to the CNN model. The idea of the CNN model, all the different steps have been already part of lecture 6. So I will not go in all of the details, just a couple of them that are relevant for your assignment. I talked about K-fold, for instance, and so on, validation splits, and so on, but also optimizers will play a role later. However, we firstly observe now we have essentially this interesting, Amazon service here, this notebook on this instance, which is T3 medium, not very powerful, right? So this is something we already know. And let's say when we now execute this, there will be lots of, let's say, configurations now starting when we have the first cell executing. Always remember when you do your assignments and so on with Jupyter Notebooks, we really need here something where, there's not anymore a star if you continue, right? This is an important part for those that don't use Jupyter very often. Then we execute here the different steps. We have the loading of a data set just as different functions defined here. Nothing is done really. We have talked about how we basically now change the idea to a convolutional 2D network here. Still the dense layer, if you remember, is at the end. We discussed this many times in the on the conceptual lectures. The softmax extends to give us probability. And we have, of course, this 10 classes here that we want to get out of it. We have a specific loss defined for this, a categorical cross-entropy loss, which is quite good for this classification tasks. And you see also SGD as a stochastic gradient descent, the optimizer we can choose from. And you will see that this is one part of your assignment also to think about, that here you have different optimizers you can choose from. This doesn't mean a lot of coding, right? You just have to exchange a little bit the parameters to differentiate optimizer. And if you see on the top, you will already see that some of them are already basically imported for you that are also relevant for your assignment. So hence, play with the code a little bit, not redeveloping it, of course, would be one goal. And we want to show here more or less just the computational complexity now in the practical lecture. Hence, we have here many functions we define, and we basically have a so-called test harness now that we want to use, and then where really the idea starts with loading the data set, and then basically go with the so-called cross-validation through the data, perform model selection several times. Hence, we call here the evaluate model, which is then training the data set according to different splits. And I come all of this a little bit as an explanation later. So let's start now the idea of running. And that's now the interesting part. So we firstly see no CUDA capable device detected. And that is true. If you remember, we had just an entity which, is a very cheap CPU entity. We see now, the epoch 1 of 10 is actually computing here. And as you can quite see, this is quite an elaborate task, especially if you think about that this is a toy problem, right? This MNIST data set. I mean, it still captures the essence, but now think about that we have, again, remote sensing data, that we have large data sets. Then we really have a problem. And also you see the number of epochs, right? So we have epoch 1 done. We define 10 in it's one of our basically parameters to train. But here you can then, it takes 33 seconds, right? Again, the accuracy that we obtain is not so bad, but still after one epoch, we cannot expect very much. So we expect that by doing so, by waiting and waiting over this 10 epochs, we also want to increase in the accuracy. Now, while this is happily computing, and again, I draw your emphasis really on this node, right? So this is sort of 33 seconds, 41 seconds. Now we're slowly starting epoch 3. The CPUs really has their, challenges. And in some respect, if you now think about, you would do much more epochs to go through the data set, then you may be even in trouble here. But let us come back a little bit to the slides while this is happily computing. Hence, I marked you a little bit. The training time indicates already for us the need to GPUs that we don't have here. Right, this is what we basically have here, the little instance, and we want to change that perhaps later. One way of changing is, of course, a little bit what you should explore in your assignment. I will not make a big demo here, but I have some important considerations just here that you differentiated a bit, of course, from the Amazon SageMaker I will present here for the larger audience, also in YouTube, because there are people from industry also in Iceland that are looking at these lectures and also want to maybe use the SageMaker tool on cutting-edge infrastructures, and we will come back what that means in a moment. But of course, for you, as the students, the Studio Lab service is quite good. Firstly, because it's a Google Colab similar service, if you want. So it's something that provides you nicely. You see that here with free CPU and free GPU resources, right, on the computing infrastructure. Also, the whole sign up is different. You don't need a credit card. You basically can easy, go in there and do your notebooks in a fully managed service. This is really, so to speak, more as a training setup. And with this, much more easier than using SageMaker as I do, because I swipe my credit card for the demonstration you see basically today. And hence, we don't want to do this with students. In other words, and you know that already by looking to the assignment, the Studio Lab service is something where you have to request an account. It's free, as I said, no credit card needed, but it's a quite nice IDE. So that is another important part for students, I guess. The complexity of the Studio Lab environment is much reduced. Right now, if you come back maybe to the overall services here, just as an example, the rich set of services that you have here in Amazon can be overwhelming. Right, you see here lots of different services that are available that we already have used in the course, indirectly or directly, with EMR, S3, EC2. But take away the message that it's much, much more out there, right, in all of these different areas and so on. And the idea of using the Studio Lab is really giving you a kind of nice isolated way of it. And as I said, also you see here costs coming for me, not for you, luckily, when you use then the Studio Lab environment. Hence, explore this please early. That's important because there's a sort of verification process. There's actually two verification processes. One is that you have to request an account, and they come back to you with an email that you have to click on. So I go quickly through this. You can, I think, perhaps some of you have even done this already, can then quickly verify your email, but that's not the end of the story. So usually you have sort of a waiting list. So it can be that this can take a little bit of time. That's why I said, please do that early now, wait for the deadline, 1 day before the deadline, and then create an account, right? So this means maybe a little bit of waiting time. In our experience, that can actually vary quite much when basically you get the account. But when you get it, of course, you can log in. And there's already, while you maybe wait for it, you can already look a bit in the community area on it. So I think that's also a nice area with it, especially if you learn machine learning, if you start to basically interact with others, maybe using other examples, from others that you see here are available on GitHub. Particularly tutorials for you as students might be beneficial. And then, of course, I think almost everybody in computer science from you here in this course knows Stack Overflow. There's also an area on this Amazon SageMaker where you basically can discuss and also get, let's say, some answers to your questions if you are stuck somewhere. So there are videos. It's a rich resource in one respect, really, for teaching, training, get used with it. But you can also immediately understand, although it provides you these resources, right? So GPU for up to 4 hours at a time. And this has been a bit changed. It's now in a 24-hour period, and you have to choose it. You see, much more simpler. You don't have to specify now exactly which GPU. Is it a kind of Hopper card? Is it a kind of Volta card, Ampere cards, all these different generations of NVIDIA cards, for instance, that we're going to pick in SageMaker later. But this is quite nice. You have to do this. This comes just with one interesting element. Of course, firstly, you should be well aware that GPUs is just for specific tasks. So we are bringing into our mind our idea of training a convolutional neural network might be something where we need GPUs, coming back maybe also to our Jupyter notebook, which is now running on CPUs. We can see that the system is still happily working on all the different epochs. Right, and this has something to do now that we go several times through this based on the folds of the data. that you have here to implement this K-fold I will allude to later, which is a validation technique to really reuse the data in the most optimal way. But the key message to really take away is ignore a little bit perhaps these errors. It's clear that there's no CUDA capable device here, but it's clear that this means directly CPUs, and in other words, also slow running time. Hence, this is still running and running and running, which is, I think, also the learning experience I wanted to bring across here. So that's good, that still runs. And it also shows you this answer. So if you do it in your assignment, of course, I think the GPU would be right for you, right? You see also that, of course, some parts of the assignments will be CPU versus GPU, that you experience the same thing that I present right now, right? So try your luck with using a CPU with a CNN and see what happens. Note the time. You don't need it really on a millisecond, the training time that is basically there asked for. Just take the time, let's say, reasonable in terms of seconds or so. There's one challenge potentially from previous experiences. That means the mobile phone number is needed, and it seems to be that not all countries are supported. So especially Erasmus Mundi students, particularly those which are maybe not in the European context, also there might be some phone numbers which are not supported. And in this regard, we have a plan B prepared basically for this assignment. And then we will discuss it via our chat environment and the threads, who then gets access to the other environment. This is unfortunately a limitation of SageMaker Studio Lab that we can't steer. And we have to look case by case on the different teams where it works and where it not works. But we have other resources in Jülich where you also can experience the difference between CPUs and GPUs. So this is the idea of your assignment, and in the way, something for really beginners to work with, the Studio Lab environment. But let us now come back to the real idea of learning from it. What is now the power of GPUs in this, and where, of course, you can imagine technology plays a big role in terms of generations, right? So you see here quite nicely the different generations of NVIDIA GPU cards, starting perhaps with the Volta line in the Tesla cards, with the V100s. We have used a lot a long time ago in a way. But then the A100 Ampere cards were already much more advanced. The Tensor cores, they're basically faster and more capabilities. And now the really cutting edge that you see here in the P5 instances, because here you see all the different generations from NVIDIA reflected in the P3s, in the P4s, and the P5s. You basically see the nice generations that you have in all of these NVIDIA cards. And this is the Hopper 100 cards, which are now the let's say, cutting edge right now in our community. You see a couple of other information which is important for interconnecting GPUs. One example are NVLinks, where you can actually connect different cards together. So they have a very specific link together, which also increases the performance if you go multi-GPU. And the same is actually true for NV switches, which are a little bit, let's say, bigger in that regard. But this is something we teach rather in the HPC course, to really learn GPU architecture, to learn how the interconnects are, and so on. Of course, for cloud, in a way, you don't need to know that right now. That's the beauty. Of course, still for the SageMaker, you have to choose which instances you want for your services. And you can immediately see you go there, and as I always say, you have to pay the price for it. Right now, when we talk about P3 instances, you see here one that we're going to use with $30 an hour. That's already something, right? It has also quite nice non-volatile memory here, compared to maybe others which have just other storage options. But you see also, when we increase now in the, let's say, generation of GPUs, you see from, let's say, the Volta, which is a bit older now, to the Grace Hopper cards, to the cutting edge NVIDIA GPUs, you not only have, of course, much more power, much more memory, and so on, and also storage memory available, plus performance, you also pay 3 times the price roughly, right? So in terms of, $31, you go quickly to 90, or let's say, bluntly speaking, $100 an hour. And that can be quite some cost, right? Of course, you get quite nice 8 NVIDIA GPUs, which are extremely fast, and also can, of course, accelerate your business a lot when you train new AI models. And here, hence, is a relationship to the costs, the relationship also why we as university cannot give you now as the assignment Hopper 100 cards, because 1 hour or $1 an hour is still a lot of money also for a university. You can imagine this quickly accumulates depending on when people do the assignments over a month. Hence, you have this kind of studio lab interface, right? So please don't mess them up, right? Don't go for the assignment, swipe your credit card, go to Amazon SageMaker and do now P5 instances, right? As student, and then try to reimburse it with me, please not. Rather, consider the Studio Lab service, and if it doesn't work with a mobile phone number, we will find a solution. Hence, we want to talk really about the real production one that you would also use when you maybe go to a company. And there's, of course, lots of, description around it. You see here when you go to the Amazon EC2, in order to convince, your bosses or your CTOs in companies. There are now examples. There's, of course, a good overview from experts given to you in order to make the money available for these, right? And of course, then you have to choose. I choose here one that is a bit older. You see the V100 that I made the case for before. 8 V100 cards is still powerful deep learning possible with these cards. And this is something we're going to use here now as an instance type of the notebook, right? So now when we go back to the practices, we see hopefully that our CNN is still busy, right? So we are now computing again another epoch according to the folds. We see we don't really improve here much in the speed. And I want to take this opportunity also for a couple of things. So firstly, we are back here in the Amazon workspace. We have the Amazon SageMaker already discussed. And we have the different regions that also play a role with this, right? So when we now see that essentially we want to go to the notebook that we have here already running with this interesting instance, we maybe also switch regions. And I have prepared here, for instance, North Virginia, because they have also this kind of interesting, let's say, V100 cards available in this particular instance, right? The one that I picked that you have also on the slides with a particular cost item of $30 an hour. So this is what we want to choose, what I have already done there. The way how to create a notebook was documented a bit before. So essentially all what we change is just the instance type, right? So instead of having this, do you remember the small T something medium small resource? We now have cutting edge 8 GPUs, maybe not top notch Hopper cards, but V100 cards, still good enough for us for doing deep learning in a toy application problem like MNIST. Hence, now I also start the open the Jupyter Notebook. Hence, we will be now noticing that we have another name for this. It's called CCBD Notebook GPUs, right? While I still, of course, have the others running here, which were the notebook USEs we had done before the CC Notebook 1. And this is still happily computing in the cloud, as it should be in parallel somewhere else, because now we are in a different region. So when we now come to the idea of thinking, we have now this beautiful resource, it's running. We also want to use it, right? So basically, you see just on the slides, almost everything I will also talk here and demonstrate you. You upload this different ANN and CNN. I skip here the data understanding script that we had before, because you can imagine this is a very, very tiny computing element. So there it doesn't really matter. And for saving money, I would even suggest for data exploration and data understanding, often it can be enough to think about, doing this rather on firstly, maybe just your laptop, if possible. If it's large data sets, you might still go to the cloud, but you don't need the cutting edge GPUs for really inspecting the data. The GPUs are needed for the training, right? So this is an important differentiation. You see also the move we done to North Virginia here on the top, for instance, and in order to get access to this particular resource. Hence, not all resources are available in all of the different regions, which is another important part of this. We have uploaded this, and of course, we want to understand what happens. And of course, in the light of time, I already created this instance. That now we have to make sure that we use the correct one. You see here, that's notebook 1. That's not the one that we want. We want basically this other one, the notebook GPUs. I go to the CNN model, and we will see there that I basically executed this already. So I will restart and clear the output here completely. Now, as the source code always has some interesting surprises when you upload this, there will be still some, warnings. It's not cutting edge source code. We try to port this between different, let's say, cloud vendors and so on. But that's not the message here. We don't do this for the software engineering discipline of having perfect code. I rather want to show you here the running time. So hence now, when we go here, what we don't want to see anymore is like there's no CUDA, right? Or something like this. So this is something where is an important part. So no CUDA devices detected would be not so good. Then you have the same idea that we just had. We defined several of these, helper functions really, that we will discuss a little bit while this is all training and running towards the end of the lecture. And again, we could do many different things that you want to do in your assignment, hopefully changing, regularization, changing validation a little bit. But the key point now for you is to understand what's happening now. Right now we're running this training and the epochs will soon start. And you see some warnings. Okay, that's sometimes there. It has something to do with smaller configuration options. But when you're now thinking about the epochs, right, you already feel what's happening. Now we're talking about 2 seconds, 2 seconds, 2 seconds. And you see that the progress bar is almost like, slower than the progress of the training itself, because we, have a visualization of a computational process. So it's always lacking behind what's really happening. And, here we go, from epoch to epoch based on the folds that we had here, right? So for this for loop, we go now again through this, training it with, just different data sets that I will now allude to in the remaining time. But I think you already get away now the message. We paid $30 an hour instead of 0 point something cents. But what we get is that the training is much more faster, right? We're talking about really seconds for a whole epoch to learn. And of course, we want to do this by not losing accuracy, right? You see also the accuracy still follows through. And this is the beauty element of it. And when you now come to larger data, the NV links will ensure that you still have quite a very quick interconnect between the different GPUs, especially also the NV switches on a larger scale. And then you can really do, let's say, an enormous speed up in the clouds by using this. Let's just, for curiosity, come back to the ANN. I mean, all what I described here is a little bit in. We basically see now that by all of going through this, this is a lots of, as we said before, these epochs are characterized by lots of matrix vector multiplications or matrix multiplication, doing the weight updates, then compute again, doing the weight updates, basically back on the backpropagation and the chain rule and so on, things which you rather need to learn in a proper machine learning course. But you see also the quick update of all of this. So for curiosity and to save some time, I want to do this also with the ANN. So let's see if we can improve, basically also on the artificial neural network speed. We were having this in the last time where we thought, okay, this was boring slow, right? So let's see what happens if we do the ANN. And also we use the GPUs here. So it was, of course, less computational complexity. This is not a 3D convolutional. We are back to our, basically 2 hidden layers that you see here, densely connected. So actually no deep learning if you want. But we have experience in the last part that this was already from the fitting, which is now started here, still slow, right? But what you see here now is that it actually gets almost immediately done, right? We're talking about 0 seconds, meaning it's basically below the seconds of doing these epochs, right? While if you now look back to the part 1, we were waiting, and so on. So this shows you again that, of course, the idea of neural networks and the backpropagation of error, while not here also then, of course, losing accuracy, just because we have now GPUs very distributed, of course, across the tensor cores of the many core chip. So something we learned in the beginning of the course. GPUs are many core devices, lots of cores, but on a moderate performance, but enabling massively high throughput. And this, basically matrix vector multiplications I'm alluding to here is then something which was really getting accelerated a lot, because you can nicely parallelize this beautifully. Having shown you these points, and we will make the case, I think this is still running. Probably I come back to the CNN model and the CNN model in GPUs. No, it's already done. You see, that's the beauty of using GPUs. And we have here the nice area of seeing the training where the cause entropy loss going down. The same with the classification accuracy here going up. These are the epochs. This is the error, or here's the error rate on the left side. Here's the classification accuracy on the left side. And here we have the number of epochs. And you also see a little bit sort of the notion that we probably cannot advance if you do 20, but that is part of your assignment to find out, right? So where are you with this when you do all of these different movements, these different changes in the code? For the time being, I'm not getting into it. And no matter what you would do with regularization, validation, and what you basically should do in the assignment, you will realize that it's basically probably not possible to go to 100%. And one of the reasons I give you before is probably these cases where no matter what you do, how well you basically craft your neural network, even how many CPUs, GPUs you throw on the problem, there are some data aspects which are just so noisy that even humans have, problems of understanding what kind of, characters that should be. So basically finalizing this, making the conclusion here, the output varies sometimes a little bit. Of course, the optimization is something which has some fluctuation. So maybe sometimes for papers, for instance, we would run all of that 10 times, take averages, because this is, of course, a process which is not really completely deterministic, right? So always the same, because you pick certain assumptions. It's a statistics inherent problem, if you want. It's a statistical learning that we do, and in the end it has some changes. But the order of magnitude shows clearly the CNN is, of course, the best solution that we had from all that what we had in lecture 6, 7, and now the practical lecture 7.1. So coming a little bit back to the idea then, doing this in the cloud, and what would be now the idea, you have to see that the kernels are right, that they fit to your application code. Hence, we need a TensorFlow kernel. But other than this, the cloud can really help you a lot. We already made the move to the artificial neural network. That is what I showed you here again, that now suddenly we talk about 0 seconds. If you now compare that to the part 1, where we were almost fall asleep when this was training, this was on a CPU. Now with the GPU, thankfully with this new notebook with $30 an hour, this neural network is trained in an instant. So, and this of course showed really also the rising of artificial neural networks suddenly with the new technologies that we had. Now, the final couple of minutes, I wanted to talk about a more complex part in machine learning, and you have already touched across this a little bit. So firstly, we have lots of parameters to train the dense layer here. The weights are lots of parameters. They all have their biases. And we do this 10 times because we basically have 10, basically classes here to do. 7,800. We had the basically hidden layer network with 118,000 parameters, a big increase already, 2 dense layers. Everything is connected with everyone in the neurons. And of course, I can pick now different number of neurons in these hidden layers that will basically increase or reduce this number of parameters to learn. Same true for the CNN with 1.2 million basically to learn already. And there you can understand now why the GPUs are making such a massive difference, because here the jump from this huge amount of parameters to train is quite a lot. Now, an important part for more experts is that differentiate parameters with hyperparameters, or weights with higher parameters, right? So these are the weights we learn, the parameters we learn of the neural network. The hyperparameters are a bit different. You would pick a specific learning rate, a specific momentum. You will actually pick ADAM or SGD, RMS prop, another optimizer. You will maybe even have another error measure. I mean, that's not what you should do in the assignment. The category cross entropy is quite nice. But still, you can also switch the number of epochs. That's what you should do. Also assignment and so on based on the CNN model, and then play a little bit around with validation, what I will tell you next. The question is, can you beat these numbers, right? So is there something when we play around with the number of epochs, let's say you have 200 epochs, can you increase? Or don't we show in the graph already maybe there's a sort of, early stopping necessary, which is one of the regularization techniques in machine learning before you start overfitting, right? So 200 epochs might be not optimal, and you should also explore that a little bit when you do your own assignment. Batch sizes. So there are lots of parameters where basically this is something the human picks, we pick. And that is, of course, something then where we don't know exactly for this particular application which might be the best values. Hence, you would basically perform a model selections on this, and that's where validation is for. That has a certain essence, and I show you here a little the overall view how that works in machine learning. Again, the different hypotheses that we have actually used. Here's the multi-output perceptron, tool hidden layer ANN, and also CNN. We would use the training set, train on all of them. And usually what you would do, you would have a validation set, right? You set that apart. It's not really part of the training set, but it estimates the error if you would have a test set. So it's another name for a test set. The test set is still there. We wrote that in the corner, but we validate and perform an estimate on the error. You see that here on the validation set. The reason is that we need to decide on these. And once we decide on one of these models, which would be probably the CNN, we basically have done a decision with a positive bias leaving behind in the data set. So we use that for an, let's say, a decision by human. And so it's contaminated, as you would say, as machine learning experts, right? So hence there need to be special techniques to basically fight this contamination. How you then would proceed, of course, is by using then your favorite model, a specific model we choose from, with basically based on this validation set where we trained on, in order to get an unbiased estimate. Now, what would be the best model? And of course, now in the end, you throw everything in the pot again, the final training on the full set, where you then basically get the real out of sample. And then that is the one you, of course, confront with a test set, right? To get the final accuracy. So this is how machine learning would work. Let's say if you have enough data, if big data is there, you maybe want to pick 5 validation data sets to do more model selection techniques. But usually we don't do that in machine learning because we don't swim in data. Annotated data like MNIST, where you have very nice supervised labels, or in remote sensing, is this pixel water? Is this pixel earth? Is this pixel maybe a building? These are very costly data sets where people have go into these places, annotating, labeling these data sets. You can imagine a very elaborate element in all of these creation of supervised learning models. So, and mostly of the data sets. Hence, they usually are very rare. And we have a technique that you also see a little bit already in the CNN. I just want to allude to, because cross-validation on validation itself is basically 2 university lectures, right? To put it correctly, it has something to do, again, with statistical learning theory. It has something to do with the limits of training samples. We use them for training, we use them for testing, but you have a certain level K here that I want to say is now the trouble that we also have to cut away basically some of the training samples for validation. Now, when you remove something for training, usually you may be also underfitting eventually, right? So you not have enough data to train. Equally, when you have less samples to test on, then you come with an estimate of error, which is not really reliable because your testing set is not large enough. So I have a constant conflict in production or in your real applications among these 2 lines here, where to put it, how to use it. In order to cope with this, an interesting smart technique has been created, and I just leave that here for a while because we will come back to this a little bit in lecture 13 with more details. You would have something like an n-fold validation. So you would always pick, let's say, take 1 out. Oops, that was a bit too fast here. So we use 1 for validation out of these, let's say, 10 parts of it, if we do 10 folds. And then we use 9/10 for the training. Then we put that back in the pot and then use the next one for validation and the others for training, etc., etc., etc. So you basically come to the idea that you train the model more times than just once, right, with a training set, by using this cross, fold validation. And this is also part of your assignment. You will see the training time. It takes a bit longer to do that. As I was demonstrating it with GPUs, much more faster. If you do it now with a CNN model on CPUs, good luck. So that will take some time. The best way of doing it, maybe a one-fold. That would be extremely computational intensive. You can imagine we always take one sample out for validation and train on the others, then a next one in, and we repeat. So we would go with one-fold through the data set. That means many, many runs. So also computational challenging. But in a way, I think, given the time at hand, I can, of course, talk many hours more, but we also want to advance in other topics in machine learning, basically, and also in cloud computing and big data the next couple of weeks. So while you're busy with your assignment, we will clarify more IAAS, PAAS, and SAAS in the next couple of weeks. And we'll come back a little bit to machine learning and data mining then after that. But in the moment, that's really all from the practicalities, and see you next time.